Okay, so standard deviations, remember, tell us how far a value has deviated from the mean. Now, we can express standard deviations in terms of the units that we have gathered for our dependent variable, but you'll also notice, like in the previous slide, we also can represent standard deviations as 1, 2, 3, or -1, -2, -3. These are examples of what we call standard deviation units, meaning it's just 1, 2, or 3, okay? In terms of the actual units, your value might assume something different. So let's say that our mean was 10 and our standard deviation was 5. 10 would exist at the mean, right, in units of what we have measured. One standard deviation above that, or 10 plus 5, would be 15, so that would be the raw score that exists at the one standard deviation from the mean. We could then add our standard deviation 5 again to get 2 standard deviations from the mean, which would be 15 plus 5, so 2 standard deviations from the mean would be 20. Plus 5, we would get 25, right? If we went below the mean, we're subtracting our standard deviation in the units that we measured. So starting at 10, minus 5 would be 5, minus 5 would be 0, minus 5 would be -5. So I go through a video that kind of explains all of this, but just conceptually knowing, if we're looking at standard deviation units, we can also kind of coincide these with z-scores, or what are known as z-scores. And one z-score is equal to one standard deviation. So if we're at plus 2 standard deviations from the mean, that is also equal to 2 z-scores. The formula to calculate the formula to calculate z-scores are basically the same for a population or a sample. The only thing that changes are the symbols that are used. For our class, we'll always be working with samples, so we can just go off of this, right? X being a raw score, X bar being the mean of your sample, SD being the standard deviation of your sample. So again, these are the 3 ticket items that you would need to know to calculate a z-score. This is going to help us determine the probability that a value lies, and I loosely use this, less than or equal to a certain raw score of interest. Okay? In other words, it's the area to the left of a given z-score. So if we go back to this slide, calculating a z-score gives us this picture, right? We have a raw score of interest, and we're given the probability that the value exists at or below the given raw score of interest. Okay, so less than or equal to, you'll see in the activity where I use this loosely, but for some people it helps to visualize. You just think at or below. So the area from the raw score and to the left. Z-scores are also a type of standard score, so the other type of standard score we've already mentioned so far in the lecture series is our coefficient of variation. So in other words, it doesn't matter what the units are that you've measured, a z-score is a z-score. And the z-scores will be the same for any calculation that you run, regardless of the units that you have collected. Now, to use z-scores, we have a z-table. Okay, and it looks something like this. I have a PDF version that is more legible, but just so you get an idea of what the table looks like. We have both a positive z-score table, which will give us all of the values from the 50th percentile to the 100th percentile, and we have a negative z-score table that gives us the 50th percentile to the 0th percentile if we're moving down to the left. Okay, which should make sense, right? Because when we plot our distribution, if we have a normal distribution and our mean is in the center, when normal distribution, the mean, the median, and the mode should all be equal to each other. And we know the median is associated with the 50th percentile, or the middle value in the distribution. So that is why we get the 50th percentile down as negative values, or minus 1, 2, or 3 standard deviations below the mean, and the positive, or plus 1, plus 2, plus 3 standard deviations from the mean as the 50th to 100th percentile. Again, we'll talk about percentiles next week, just kind of bear with the topic for right now. But just to reiterate, because this is the concept that everyone always forgets, the z-scores give you the percentile under the curve to the left of the z-score. Right? That area under the curve, again, represents the probability that you have randomly selected a value at or below than your raw score of interest. So, how do we read the table? When you get a z-score, you're usually going to calculate it up to 2 decimal places. You notice this first column here lists up to 1 decimal place, or the 10th decimal place. So you'll find your z-score based on what you've calculated, find where that exists. Let's say we had 1.83. So on my table, I would go to 1.8, and then I would go to the column that has 0.3 as my hundredths place. That value, or all of these values rather, represent the probabilities that a value exists at or below them, the raw score of interest that you've calculated your z-score for. Right? In other words, the area to the left of the curve. So, again, just to visualize a little bit differently, negative z-scores, again, are going to be associated with negative standard deviations, okay, and percentiles between 50 and 0. So just so you get associated 0 to negative 3, right, 50 to relatively 0. Positive side is going to be the area to the left, again, so I have both of these arrows pointing the same direction so that we get it in our heads. We have the area to the left, right? But those are going to be positive z-scores or positive standard deviations from 0 to 3, and percentiles associated from 50 to 100%. Okay? I want you to note also we use z-tables when we're estimating percentiles. Okay? We say they're estimated because we are assuming that the sample data are normally distributed. So when we calculate percentiles in various other ways next week, those ways are going to be exact percentiles because we're using all of the data that we have collected in its rawest form. Estimated percentiles because we're using the mean and standard deviation. Remember that those two calculations are going to be affected by extreme scores. So if you have an outlier either above or below the mean in any of your distribution or data sets that you're working with, that could skew the mean and standard deviation, and if not caught, can affect the estimated percentiles that you calculate. So that's why we say z-tables give us estimated percentiles. Using other methods to calculate percentiles would be methods for exact percentiles. But again, that's next week. I wanted to give you guys practice in the lecture. Okay, so if you need any help calculating or performing this activity here, I have linked a help video in your PowerPoint to YouTube, so you can watch that, and I walk you through all of the steps on how to calculate this. But basically, you're just going to be using the z-score formula on these 3 raw scores, and then you'll use your z-table to estimate percentiles at those given raw scores. I've also included a solutions slide so you can check your answers, especially if you're doing them on your own and you want to see if you got them right. So feel free to practice those as many times as you like. You can also make up different raw scores that might exist in this distribution, and you have more practice. Okay. The next thing I wanted to talk about was constructing a distribution. We will have questions that pertain to constructing a distribution on the exam, so do make sure that you do all of the practice problems for this, because it is a challenging thing that some students just don't really grasp onto. So I've included more practice problems in lecture this semester. I'm hoping that helps. But these are the basic procedures that you would use to construct a distribution. You start by drawing a normal curve, assuming that you have a normal distribution. Okay. You're going to notate where the mean is. So generally speaking, we should put that in the middle. You can either note it as a standard deviation unit, which would be 0, or you can put x bar, or you can put mean, or you can actually put the mean in the units that it's been collected in. In this example, it's VO2. And then from there, you notate plus or minus standard deviations in either the units of measurement or the standard deviation units. So in this case, we can see that our standard deviation is 5. So you can either say 60 plus 5, 65 plus 5, and keep adding 5 as you move to each standard deviation, or you can just stick to 1, 2, and 3, and minus 1, minus 2, minus 3. Doesn't matter. You then locate the position of the raw score of interest within your distribution, which usually I give you the raw score of interest, and then you would shade the appropriate region based on kind of the goal of what you're trying to find. So remember that we can either look at a percentage of values below a raw score, above a raw score, or between two raw scores. For our example of values that exist below or lower than a given raw score, let me get a pen, and we'll do red. That's cool. Okay. So the first thing is to draw a normal distribution, and please excuse if this is messy, but I'll try my best. Whee! So normal curve. We then notate where the mean is, so again you can either write 0, you could write x bar, you could say x bar is 21 and write the actual mean. Okay. For this example, we're saying that our dependent variable is the weight in pounds lifted in a bicep curl, and what we want to know is the probability that a person can curl at least 10 pounds. So we have a mean of 21, we have a standard deviation of 6.46, so personal preference, I like making 3 tick marks, 1, 2, and 3, and this is plus 1, plus 2, plus 3 standard deviations. Then you do 3 tick marks. Please excuse my non-straight line, but this is how it goes when you're drawing with the mouse. Okay, and then we have minus 1, minus 2, minus 3 standard deviations. This is totally fine. Or, alternatively, you can take your handy-dandy calculator and you can say 21 plus my standard deviation of 6.46. So 21 plus 6.46 gives us 27.46, and then you would write 27.46. And then taking that number, you would add another 6.46, and then we would get 33.92, right? And then you add 6.46 again. Going down this way, right, you could have 21 minus 6.46, which would give us 14.54. Okay, and then you subtract 6 from that, or 6.46 from this number, you get minus 2 standard deviations in terms of the units you've measured, which would be pounds, right? Minus another 6.46, you kind of get the picture. Okay, so you can write in standard deviation units or in the units of the variable. We want to know what the probability is that a person can curl at least 10 pounds. So, in the scope of our values here, we can either find where 10 would exist in our distribution, or we can also calculate the z-score. So remember, z is equal to x, which is 10, minus the mean, which is 21, divided by the standard deviation, which is 6.46. So if we calculate this, we get a z-score of negative 1.9. 1.70. From here, we then can look at our z table, right, and find an associated probability with negative 1.7. I'm not going to do that just yet because I don't want to X out of my PowerPoint, but you guys know how to look up negative 1.7. I just want to show you how we would look at it in a shaded region. So negative 1.7 is going to be between negative 1 and negative 2 standard deviations. Let's say it exists in a cyan color, and it exists here. Okay, so this is where 10 pounds would exist and or 1.7, negative 1.7 z-scores. We're interested in the probability that a person can curl at least 10 pounds. So that means I'll fix this on your PowerPoint, but this should say at most. I was copying examples, so I'll just fix that now. This should be at most 10 pounds, so meaning they can lift 10 pounds or less, right? Because we're looking at lower than a given raw score. The probability that they can do that would be the area to the left of the z-score. And the z-table is going to give you the probability or the area under the curve to the left of this z-score. Okay? So if we were I asked you, construct a distribution. These would be the steps that you would use to do that, given that we're looking for something under or below the mean. Or not below the mean, below a raw score of interest. Now let's do another example, but instead of looking at values below a certain raw score, we want to look at what's the probability a person can curl more than a certain raw score. So we'll do red pen color again. We have our distribution here. Again, we do 0, plus 1, 2, 3 standard deviations from the mean, and minus 1, minus 2, minus 3 standard deviations from the mean. In this example, we have the same mean and standard deviation. Okay, so we can easily calculate our z-score to find the probability that a person can curl 15 pounds or more. So raw score is 15 minus 21 divided by 6.46. So we should be negative again. 15 minus 21 divided by 6.46 gives us negative 0.93. I'll round up. Okay, so in our distribution, 0.93 should exist between 0 and 1. Let's say it exists here. Okay, so that's this guy, and or is also equal to x is 15, which is our raw score here. If we want to know the probability, right, that we have a person who can curl 15 pounds or more, we're describing this region, right? Because as we go up, we get greater pounds or greater weight. Remember that when you look this value up in the z-table, though, the z-table is going to give you this region. Okay, so again, z-table, when you look this value up in the table, you're going to get this region. However, we want the blue region, right? So when you're calculating the probability that exists in this blue region, you have to remember to either do 1 minus the probability, let's say P is represented by this area over here. You have to do 1 minus P to get the probability that you're looking for. Whoops, pen color cyan. That will give you your shaded region, which is here. Okay. If you're looking at your probabilities as percentages, you can easily change this to 100 minus the probability as a percentage in the green region, and that will give you this other region, right? Because we can look at our distribution from 0 to 100%. So whatever is in one region is not in the other region. So that's how we can kind of justify. So this isn't a number, it's just the shaded region, right? 1 minus what you get from reading the z-table will give you the probability greater than your RAS score. I also wanted to do an example if we're looking at a region between RAS scores. So I'll change my color back to red. We'll do our normal distribution. So we have 0, 1, 2, 3, and -1, -2, and -3 standard deviations. Okay. And this time we have, or we want to know the probability that a person can curl between 20 and 25 pounds. This means we need a z-score for 20 and we need a z-score for 25. Okay, so z-score for 20 would be 20 minus 21 divided by 6.46. The z-score for 25 would be 25 minus 21 divided by 6.46. Okay. If we do these in our calculator, we get negative 0.15 and 0.62. Okay, so one positive and one negative. And I'll do these in different colors, so this one will be cyan. So negative 0.15 is relatively going to be about right here. So that's this guy. Okay. And the probability that we get from our z-table when we look up this value is going to be noted as this region here. Okay. Now I'll change my color to, let's say, magenta, and that will represent my z-score at 25. So we have a 0.62, which is relatively halfway between 0 and 1. Okay, so this is where 0.62, or if we're looking in terms of our units, 25 pounds. When we look at the z-score in the table, the probability that we get from the table is going to be this region. Okay. Now, if we are interested in the probability that exists between 20 and 25, what we have to do is we take the probability of this purple region, and then we which is from here all the way down, and we subtract the blue region, so that what we're left with is this piece here. Okay, and this is what we get, or this yellow region is going to be the probability between 20 and 25 pounds. Okay, so you take the probability at 25 minus the probability at 20, and you end up with the probability between 20 and 25, which is my yellow shaded region. Okay. So again, you guys can actually look up what these probabilities would be. I have included some other examples with linked videos in your PowerPoint so that you can go through those on your own, actually deal with finding the probabilities using the z-tables a little bit more, but just in a different way. than we already have. And then if you click to the following slide, I do give you the solution with the shaded region marked as a red line with an arrow, and the probability that you would have gotten had you used the z-score or the z-table correctly. Okay. If you also reference the notes area of your PowerPoint, I write out the calculation using a z-score formula, what the probability is associated with the z-score that you should have calculated as a percentage, and a probability between 0 and 1. So I'll let you guys do those practice problems on your own. And I want to summarize z-scores as a whole. So again, we can either use them to calculate percentiles, specifically estimated percentiles when we are assuming we have a normal distribution. We can also use them to create confidence intervals, which we will work on in future classes, probably next week. And then we will also use these scores to calculate skewness and kurtosis. So we're bringing it back to distribution shape. Okay. We're never going to get a perfectly normal distribution when we're collecting from samples. However, to make, again, statistical comparisons, we need to show that our data is not markedly skewed or oddly shaped. So you'll notice later when we run certain statistical tests, we run the stats with the assumption that we have a normal distribution, so we must test for normality.